Okay, so I think we can start. So you have a little less than 1 hour, say 55 minutes to give us your results.
Okay. Thank you for coming to my thesis defense. The common thread of my thesis is the descent in p-adic Hodge theory. Today, I will first report my work on the canonical construction of Sen operators on p-adic varieties, and then cohomological descent for Hodgkin's ring topos. So let's start. I will focus on the aspects of descent and only mention the applications briefly. So let's start with the descent of Galois representation and Sen operators over local fields. So let me introduce some notation. So that K be a complete discrete valuation field extension of QP with imperfect residue fields. K, but with finite p basis. So this degree is p to the power d, which is a finite number. And then I take T1 to Td, some liftings of a p basis of the residue field K. And let G denote the absolute Galois group of K. The main object we want to study are finite dimensional representations, K bar hat semilinear continuous representation of G, and we would like to study this category. A priori, this Galois group G seems very complicated, and it seems inaccessible to study the whole category. But Sen gave an approach to investigate it. So let's consider the cyclotomic extension of K, adding all p power roots of unity, and then I add p power roots of the lifting of p basis. And they are all contained in the chosen adroit closure of K, and that denotes some Galois groups here, sigma, delta, and gamma. So here we see that sigma has an open subgroup isomorphic to ZP, and delta has an open subgroup isomorphic to ZP to the D. So gamma contains an open subgroup isomorphic to the semi-direct product of ZP by ZPD. So this Galois group gamma is much simpler than the Galois group G. And so we may wonder which representation of G are coming from that of gamma. In fact, we have a descent theorem of representations. So we have a category of finite dimensional representation of G with coefficient in K bar hat. And we may consider the phase change functor from the representation of gamma with coefficient in K infinity completed. This phase change functor is an equivalence because this is a perfectoid field. So by almost purity, every representation can descend to this. And moreover, Sen and Bruno proves that we can decomplete this coefficient to the representation of gamma with coefficient in K infinity without completion. And moreover, technically, we need a further descent due to Tsuji. So we can descend to the representation of gamma with coefficient in K infinity, but I have to add a condition delta analytic, which I will define later. So this phase change functor.
So some of the work was before the notion of perfectoid was introduced. I said
yes,
yes. So you are putting some later thing into
But this step, these equivalents are proved by Sen for the perfectoid residue field and proved by Bruno for the imperfectoid residue field. So the phase change functor is defined like this. Okay, so here delta analytic means that for every element of tau and every vector of B, tau x on B as the exponential of the infinitesimal action of tau of V. Here, the infinitesimal action is defined by the usual formula as follows: A times B minus B. Okay. So now, if we have such a descent, then the Lie algebra of gamma, this infinitesimal action induces a Lie algebra action of gamma on V, which is k infinity linear because we have decompleted the coefficient. So this action is linear. We know that the Lie algebra of gamma is isomorphic to this Lie algebra of semi-direct product. So we could take a standard basis, partial 0, partial 1, partial d, correspond to these components. Then we consider the infinitesimal action on V, and V extends by scalars to k bar hat infinity. So this is k bar hat linear endomorphism of W, and we have 1 plus d such operators. So this operator is called the arithmetic sign operator, and these d operators are called geometric sign operators. So these 1 plus d linear operators can be viewed as linearization of the semi-linear action of G on W, and these linear operators determine the isomorphism class of the representation of G on W. And our question is that we would like to extend the construction of sign operators over varieties, but there are some difficulties. If the residue field is imperfect and not perfect, then those 1 plus d sign operators are non-canonical, and they actually depend on our choice of the lifting of p basis.
Your K infinity is completed or non-complete?
What?
The K infinity
is not complete.
Not complete.
Yeah.
Okay.
For example, this fact, non-canonical fact, is an obstruction for our globalization. Let's consider such an example. Let's consider the semi-stable curve over ZP. We can write a picture like this. This is a generic fiber, and this is a special fiber has a normal crossing divisor. Notice that x itself is a good coordinate of A in the following sense. In the sense that if we add infinity and the p power roots of x to A and take some completion, we will get a perfectoid ring. However, if we consider the localization, let's consider the localization at the generic points of this component and the generic points of the other component, then this x is a lifting of p basis for this localization at p1, but not for the other localization. So it means that we should not only consider the lifting of p basis as our system coordinates. We should consider more general system coordinates that are compatible with localization, so that we could get a globalization of sign operators. The best we can hope is that we want to define a canonical algebra action on every representation W, that's replacing the non-canonical action given by the algebra of gamma, such that once we fix the basis of this canonical Lie algebra, then it will give us back the previous non-canonical 1 plus d same operators. This is the best we can hope. And in my thesis, we answer it positively by considering the Farting's extension of OK. So Farting's extension of OK is a canonical short exact sequence. If I had, I give it a tape twist to the Farting's extension EOK. I will define later with constant of the extended scalars of differential module. So here I write omega OK1 is the module of differentials of OK over Cp, and I give it a p-adic convolution. So here the Farting's extension is defined as the inverse limit of module of differentials of OK bar over OK. So it looks, this module a priori, it looks very large, but the existence of Farting's extension shows that this is actually finite dimensional, and it admits a k-bar hat basis. If we consider the previous lifting of p basis, then we consider the log differentials of ti, pn's power, pn's roots of pi, and they form an inverse system in this module. And we have 1 plus d such elements. Here, my notation for 0 is especially the roots of unit. So they form a k-bar hat basis of this Farting's extension. So similarly, if you take any element of OK bar and you pick up a system of p power roots of it, and you could also define an element by taking d-log differentials. So this suggests us that the Farting's extension unifies all possible system coordinates, and it should give us a good candidate for the canonical Lie algebra. In fact, we can define a canonical Lie algebra from it. Let's take the dual of that and take some tape twist. So we get homomorphism from the differentials to the head to the dual of Farting's extension, and we have finally quotient to k-bar hats. So in fact, the dual of Farting's extension has a canonical Lie algebra structure. Very easy to define. So the Lie bracket of any two elements are given by you apply the canonical linear form on one of the elements and then multiply with F2 and minus this one. This will define a canonical Lie bracket over that. Explicitly, if we consider the dual basis of this one, I denote it by P star 0 and Ti star 0. The Lie bracket between them are just the Ti star, and the different Ti commutes with each other. So here, I take 1 to D. So we see that if we choose this basis, then we obtain a non-canonical isomorphism from this Lie algebra to the previous Lie algebra of gamma. Okay. So with this canonical Lie algebra, we could define we could give a canonical construction of Sem operators over local fields. So for any finite dimensional representation of G with coefficient in k bar hats, there exists a homomorphism of V algebras. I call it phi sen restricted to W from the dual of Leibniz extension to the Lie algebra of endomorphisms of W. So this homomorphism is G equivariant and functorial in W.
Is it compatible with finite field extension of K?
Yes, compatible with. Or we can say that it is functorial in K. And moreover, this can be computed by choosing generalized system coordinates, not only lifting of p basis. So let me explain in the following. So let's consider finite many elements of K. Such I only add very mild conditions to them, such that the differentials of them, let's see, this motion are linearly independent. So these elements, we call them generalized system coordinates. And consider such elements, we could also define the tower as before. We first consider the cyclotomic extension, and then we add the p power roots of this Si. So they are
the same as D. E is the same as D.
No. We could take
Smaller.
yeah, smaller or bigger, but yeah, it has to be smaller. And we add those p power roots of Si to them. So yeah, the space is too small. And here, the gamma group denoted by delta prime and gamma prime, they are contained in our algebraic closure K bar. But if we consider such a generalized system coordinates, we may not have a descent theorem. So we need to compute the Sem operator, we need to add an assumption that we have a descent in hand. So we assume that under this space change functor, there exists a representation of gamma prime called V prime, whose space change is W. We need to assume this condition. Recall that if we consider this lifting of p basis as our system coordinates, such a V prime always exists and uniquely.
And if E is equal to D, then this should also exist.
We don't know it. If E is equal to D,
Obviously.
then we may not know. So first, the first question is that if this is a perfectoid field. Yeah. So
I think
such a
it follows from in my work on almost ring theory. So there is
yes, you're right.
some theory of the
Yes,
differentials, and one can actually, I think that one can see that this gives a way to get perfectoids.
But maybe for local fields this works, but maybe for p-adic varieties we don't know if such a mild conditions on differentials could give us a perfectoid ring.
Yeah, I'm not sure about that.
Yeah.
This was originally just for
Yeah. So for local fields, let's just consider them. Then the conclusion is that then under this condition, the Lie algebra of gamma prime is also canonically isomorphic. Is also isomorphic to the Lie algebra of the semi-direct product. And we could also take a standard basis, partial 0 prime and partial 8 prime, and this homomorphism of the algebra can be expressed by the following explicit formula. So for any element of the dual of Falcon's extension, we can evaluate f as an element of the Falcon's extension. So the log differential of Si, p power roots. This is an inverse system, and I give it a Tate-Twist. So f can be evaluated as such an element. This will give me a scalar and the tensor with the infinitesimal action of partial I prime on the descent V prime. So this is our formula. So what the theorem says is that given a representation of G, we may have many generalized system coordinates. We may have many such towers, and we may have many such descents. But no matter which descent you choose, such a formula, the value of such formula will not change. So, proof. We only need to check this non-canonical formula is independent of your choice of your descent and your choice of generalized system coordinates. So how do we prove this? We use p-adic system correspondence. Correspondence over OK divided by Suji to compute if we change the system coordinates, how the value of this formula will change. So we do it a concrete computation, and we finally find out it is actually independent of your choice of your descent and system coordinates. Okay, so now we have a canonical construction of sample operators over local fields now. Then we could generalize them to p-adic varieties. So let me change the notation. So from now on, K is a completely discrete variation field extension of 2P with perfect residue field. And let A0 denote a node ring normal domain over OK with non-zero special factor. And we assume that A0 is semi-stable and admits a standard semi-stable chart. So let's consider OK to 1 to TR plus 1 plus and minus to TD plus and minus, and divided by the semi-stable condition minus the uniformizer of K. And we assume that there is a Adler ring map to A0. And then we consider the generic fiber of A0, which is also a domain. And we let L0 to be its fraction field. We consider all the finite extension of L0 such that the normalization of A0 in L is finite Adler. And let A denotes the integral closure in L. And we denote L unramified, the maximum the union of all of such finite extension, we call it maximum unramified extension of L0. And we denote A bar inverse P, the integral closure of A0 in this maximum unramified extension. And we denote this Galois group by G, which is actually the fundamental group of the generic fiber of A. The main object we want to study are representations of such fundamental group. I would like to remark that in my thesis, I also allow ramification along normal crossing devices on the generic fiber. But for simplicity of this talk, we just.
So can you allow slightly more generally, like T0 up to TR minus the power of pi, so that it will, or you have to.
A0.
No, that's in the equation. Can you have T0, T1, TR minus the power of pi?
Can you replace pi by pi to the r?
Yeah, I think so, because in my thesis I consider actually log smooth things.
Okay.
Yeah.
So this saturated log smooth, or you mean log smooth and saturated also, or just log?
Just the log smooth.
That's
no
not
saturated condition.
okay.
Yeah.
And sometimes people consider the completion of enzerization, the p-adic enzerization instead of
p-adic enzerization.
Yeah, but here it doesn't matter because you have a good chart. Okay, doesn't.
Yeah. Okay. In this setting, we can also have a canonical construction of Sen operators. For every finite projective representation of the fundamental group with the coefficient in A bar hat invert P, there is also a homomorphism of Lie algebras from the dual of Hodge's extension of A to the Lie algebra of endomorphism. So satisfy the following conditions. So first, this is G prevariant in the functorial in W. And moreover, this is independent of the choice of the semi-stable charts on the left-hand side. And finally, this is compatible with the local field case if you do the localization at height 1 prime ideals with the local field case. In fact, in our proof, we show that this is a unique one which are compatible with the local field case. Okay, so I will mention.
Is it also functorial for maps of such things like you have got morphism
of A, different A.
Yes.
Yes. Okay, so the proof, in fact, is similar as previous. So we first need a descent theorem of W to some representation of much simpler Galois group. So this is such a descent always exists is due to Suji when he developed the p-adic Simpson correspondence for log smooth schemes. And we showed that his argument remains true if we shrink the Galois group to a finite extension. So in Suji's case, he only considered the case L is equal to L0, but we showed that his argument always.
So is there a formula for V in terms of W or no? Is there a formula for V in terms of W element in variable?
Yes. If we pick up a special system coordinates, let's say if we consider such a system coordinates, then we have an explicit formula for this. V is, V depends uniquely of W. Yeah, there is a formula. Okay, so once we have such a descent, we could produce the same non-canonical formula. Start as previous after choosing a generalized system of coordinates. And finally, we need to prove that such a formula is independent of all of our choice, of your choice of our descent, coordinates, and the chart, semi-stable chart. How do we prove the independence? We localize at one primes so that we could reduce to the local field case. Well, we have already proved that there is a canonical construction of SAM operators. So let's finish the proof.
So when you in the theorem, when you take a representation, you mean a free
Finite
rank,
projective.
finite projective A bar head over P module.
Yes, with the continuous action of G semi-linear. Okay, so I would like to remark that if we allow ramification over normal crossing devices over the generic fiber, then the canonical definition of Barton extension is very subtle. And we solve this problem by also reduce to the local field case. And then by the same strategy, localized to local field case, we generalize the theorem of Sen and Okubo to higher dimension. So their theorem about the relation of Sen operators and the action of inertial subgroups. And finally, we proved that geometric Sen operators will annihilate locally analytic vectors in A bar hat invert P. This generalized result of real time, which is the initial motivation of my work on Sen theory. But I don't have much time to explain the discussion on that. Okay, so here we see that we have already have the Sen operators, canonical construction of Sen operators over p-adic varieties, which admits semi-stable integral models. A natural question arises is that could we get rid of this requirement and develop Sen theory for generic for smooth varieties of local fields without semi-stable integral models? So here we have such a question. How to get rid of semi-stable integral model. In fact, one of the goals of my thesis is to make Farkin's approach to p-adic Hodge theory free of integral models. And I proved that cohomological descent results for Farkin's ring properties, which allows us to descend important results for semi-stable integral model to general integral models. So now I will report this work. So descent for Farkin's ring properties. So first, I will recall the definition of Farkin's ring set. So let X over OK be a coherent OK scheme. Coherent means that quasi-compact and quasi-separated. And I denote by Y its geometric generic fiber. And we recall the definition of the Farkin's site associated to this morphism of schemes. This Farkin's ring site was introduced by Farkin's and developed by Abbas and Koch. So the objects are all morphisms V to U. Here, U is a-del over X. And we consider its geometric generic fiber UY. And V is finite a-del over its geometric generic fiber. So we consider all of these morphisms over Y to X. And the topology, we allow coverings of U, and we also, they are called Cartesian coverings, and we also allow coverings of V in this direction, which are called vertical coverings. So the topology are generated by Cartesian and vertical coverings. And the structural sheaf E bar evaluated on such an object are, we can consider the integral closure of U in V. And this pre-sheaf associated with such objects to the global section of the integral closure is actually a sheaf over the Barton's couplets. Okay. So this is the definition of Barton's ring site. And we see that the Barton's site can be regarded as a fiber the set site over the a-del site of X. So over each U, a-del X in U, the fiber is the finite a-del site of its geometric generic fiber. So we see that the modules of these fibers are actually representation of the corresponding fundamental groups. So this shows that the Barton site is also suitable for globalizing our cell theory defined over each fiber. Okay, so historically, the Barton's ring site was introduced by Barton's for his proof of Hodge decomposition. And one of the key ingredients is the comparison theorem, the comparison of the a-del cohomology of Y with the cohomology of the Barton's ring site. In fact, we have a comparison morphism defined by sending every object V to U just to V. Okay, we have such a morphism, and the comparison theorem of Barton's is the following. Assume that X over OK is proper and semi-stable. And I consider a finite locally constant abelian sheaf over the geometric generic fiber. Then the a-del homology of this coefficient extend scalars to OK bar. There is a canonical almost isomorphism to the homology of the Barton's site. The coefficient in the B bar module. So this is a canonical almost isomorphism. So the first question is that could we get rid of the semi-stable assumption on X? Recall that by de Jong's alteration theorem, every proper scheme over OK has a proper hypercovering consisting of semi-stable schemes. On the left-hand side, the a-del cohomology satisfies cohomological descent along proper hypercovering. If we can prove a cohomological descent for Barton's ring site, then we can show we can deduce that such an almost isomorphism also holds for general proper OK scheme. So that's our idea to generalize, get rid of the semi-stable condition by proving a cohomological descent for Falcon's ring sites. To describe better the cohomological descent, we introduce some notions like V topologies. So recall that we still denote X to be a coherent scheme, and the Y is its geometric generic fiber. So first we recall the notion of V topology. So a morphism of coherent scheme is called a V covering if for every valuation ring A and such an morphism of scheme, there exists an extension of valuation rings and such a morphism making the diagram commutes. So for example, proper surjective morphisms are V coverings and beautifully flat maps are also V coverings. Then the cohomological descent for a-data cohomology can be reformulated as follows. If we consider the V site of coherent Y schemes, and we consider the projection morphism to the a-data site of Y, then for every Gaussian abelian sheaf over a-data site of Y, the canonical morphism from F to the derived push forward of this is actually an isomorphism. So we want analog of this for Falcon's ring sites. Recall that we have such a comparison morphism to the Falcon's ring site. So what we want to do is to find a big V site, which is analog of this, such that which admits a cohomological descent to that. In fact, we call it I1, 2. I will explain the notation later.
Sorry, to be sure, the main reason is that because in the V topology you have proper morphisms.
Yes,
So,
yes. So in my thesis, I introduced the following so-called V site of integrally closed schemes. So objects are all coherent X, Y schemes X prime. So here we recall that Y is the geometric generic fiber of X, and the XY is the integral closure of X in Y. So here we have a Cartesian diagram, and X prime is a coherent scheme over this, which is integrally closed in its generic fiber. So we consider all of such integrally closed schemes, especially the morphism Y to XY is the final object of this category. In the topology, we proved that all of such V coverings form a pre-topology of this category. So the topology are generated by the V coverings and the structural sheaf is the sheafification, sending each object to its globalization, or to its global section of the structural sheaf. So this big V site has a projection morphism to our Falcon's ring site. A morphism recall that U is a diagonal over X, and the V is finitely diagonal over the geometric general fiber of U, and we send it to the integral closure of U in V. So this gives us a natural morphism of ring site. Okay, so using this big V site, we can state our cohomological descent result for Hodge ring sites. For every integer k, this modular pk to the higher derived push forward of all modular pk is an almost isomorphic proof. The key ingredient is the arc descent of perfectoid rings due to Hodge and Schultz. In fact, if we consider arc covering of p torsion-free perfectoid rings, then the check complex is exact. And in my thesis, I proved an almost version of this, which is not purely formal. Okay, so with this result, and the second, we can see that prolocally on our Barton's rings, Barton's site, prolocally on the Barton's site, we can reach such a perfectoid because we can find the Floyd cover of U, and we can find the profinated cover of its geometric general fiber such that the integral closure is of the form spec A, such that the completion of A is a p-torsion-free perfectoid ring.
I have just a question on the before thing. So when you state this theorem, it seems that to define the map, you have to use the KP1 result, which has some history with Faltings and Aschinger did it. So, so your work uses it. It is that you don't prove it again. I mean,
we can use the cohomological descent result to give it another proof.
Okay.
Yeah.
Another proof of what? Can you?
So to define such a morphism is not easy because it's vectored through via this thing. We can consider such thing in the tensor with OK bar. So from this to this, there is actually natural morphism, and then from this to this, we have such a direction, right? Because this is equal to this replaced by the derived push forward.
By the way, this K-pi1 is for p torsion coefficients or for any because sometimes in the smooth case it's a simple arbitrary.
Because we are over the local fields, so everything matters are only p torsion because non-p torsion are killed.
Yeah, I know.
Yeah, the K-pi1 is for arbitrary.
Yeah, the K-pi1 of Aschinger also for arbitrary. Okay.
Yeah. Okay, so the K-pi1 results shows that this is actually an isomorphism. So this is due to Aschinger, and we also have an almost isomorphism in this, and this is also an almost isomorphism.
So you mean this means that locally you can find always KP1 cover?
Yes. So that
KP1 means that it's a nice.
It means that this one is locally acyclic.
Okay, thank you.
Yeah, but with our cohomological descent, we can reduce this problem to a question of V site. And over V site locally, we have valuation rings. So that this isomorphism can be seen very easily if you look V locally. Yeah. Okay, back to the proof of this homological descent. So for such prolocal thing, for such A, because we have this exact sequence and each term is almost integrally closed. I mean, it is almost isomorphic to its integral closure, p-adic completion of its integral closure. So for such A, by using this exact sequence, we can prove that this is there is almost isomorphism from this to the homology of the big V sites localized at this scheme A with coefficient O modulo p to the k. Okay, so for this we see that this is an almost isomorphism. Okay.
So you have 5 minutes.
Okay. Yeah. Yes. So let me discuss the application of the homological result, homological descent for function string purpose. So generalizations of Parkin's comparison. So we consider such a situation so that A, the variation ring extension of OK bar such that its fraction field is algebraically closed, and we consider a proper scheme over A of finite presentation without any smoothness condition. And then we denote by Y, it's denoted by, recall that we have a comparison morphism from down to the Parkin's side. Let's we consider F finite locally constant abelian shift over Y a-data. Then in this setting, we generalize the Parkin's comparison theorem. So there exists a canonical almost isomorphism from the a-data homology with the coefficient in F, extend the scalars to A to the homology of the Parkin's ring side. Okay, so this is an almost isomorphism. Proof. So we apply the Young number little z Simpkins alteration theorem for morphism of schemes. So for every x, for such a x over spec A, there exists a proper surjective map from x prime such that x prime is nice over A in the following sense, such that there exists an inverse system of morphism of schemes, of nice schemes over DVRs. So they are all nice in the sense that they are log smooth. Yeah, they are log smooth schemes over this, and this morphism is also log smooth. And the limits of them is this morphism. So for this part, for this nice part, we have Barton's comparison theorem in the relative case. In the relative case. This is formulated by Barton's and proved by p-adic. So we have Barton's comparison for this morphism. By taking limits, we know Barton's comparison for this one. And because we have proved that we have homological descent for both sides, so we can descend the comparison almost as morphism to this one.
So the map x prime to x prime lambda is what type?
There is so the limit of this inverse system is equal to this. Yeah. So taking limits, we can descend. We can have the result for this, and by homological descent, we can descend the result to x. So that's how we prove this is an almost as morphism. And then let me finally mention some applications. We remark that this V site, this big V site, is also suitable for globalizing Barton's comparison morphism, and we extended Barton's comparison theorem for log smooth morphisms to general morphism of schemes. And with more general coefficients, we allow torsion abelian coefficient and not a locally constant one. And we also use this homological descent result to deduce explicit local version of relative Hodge-Tate filtration from the global version of relative Hodge-Tate filtration constructed by p-adic and p-adic. So I think I will stop here. Thank you very much.
Okay, thank you very much. So I think we will ask questions now. Maybe we can start with Slava. So no questions.
Yeah, so I just have a couple of questions concerning the homological descent.
Yes.
So the V topology you are using is very large. So the first kind of naive approach would be to use something maybe simpler, like H topology, as long as it contains proper maps. Is that did you try? I mean, is it possible to work with just H topology instead?
You use the arc descent, and for that you.
I know. In the end,
So,
but does one really need to go all the way to perfect?
Yeah, I think we need the V topology here. For example, if we want such a comparison morphism over general valuation ring, then
now I realize that if you want to go to valuation rings, yes, but let's say that you want to prove it just for a proper map of final presentation.
Yeah. So So if we want to generalize the Barton's comparison morphism, comparison theorem in the relative case, so after we have such a result over valuation ring, to globalize it, we need a V site so that locally it is a valuation ring. If we want a relative version to globalize these results, then we need a big V site, and the H topology is not enough to reach a valuation ring. So if we start from a V site, then taking stocks, we can see that we can go back to this result.
Okay, thank you. Another question I have is that so you generalize this basic comparison theorem to any x over of what property you have proper of final presentation. Okay. Yeah. Can we somehow get a comparison theorem just starting from a scheme, let's say, on the generic fiber that is over QP? How would it look? That is, could we just get rid of the models altogether in this theory? Does it make sense?
I think so. So this coefficient, this B bar coefficient, or the O coefficient of our V sites relies on at least we should fix an integral model. So for in the scheme language, I think we should always fix an integral model. This is different from the rigid analytic varieties.
From p-adic, yes.
Yeah.
Okay. Okay. Thank you. That's all.
Yeah. Thank you.
Okay, maybe we can switch to those who are coming far away. Far away.
Okay, so with the first part, I mean, in your talk, so you claim that in the proof you first choose the coordinate and construct the universal sense of theater using that coordinate. But if you change another coordinate, so then you have to compare that. So you have to consider another extension, another k infinity, k infinity.
Yeah.
And you didn't explain that. But how can you say how? It looks really non-trivial, but you didn't explain.
Yeah.
Can you explain the idea?
So let's go back to that case. So we have k infinity k and k infinity infinity. So this is prime, delta prime, gamma prime, sigma. Okay. So we assume that we have a descent W is equal to k bar hat answer over to prime. And we define some Sen operators over that. Let's say we have such Sen operators over V prime. So if we consider another one, if we have another one, then we have the other. So we need to replace one by the other, and we need to compute out what are the coefficients. How do we compute? We consider the Hodge field ring. So the field ring is defined as the.
Sorry, delta I is not the, what did you change here? The descent or the delta I? Okay. You just assume you have two different descents. Okay.
Yeah.
Then this is better.
Yeah. So we have such a Hilbert ring, which is a Hilbert ring in p-adic Simpson correspondence. So we have an isomorphism from these two. To W. So this isomorphism is non-canonical, but so it will transfer the action of W to some Higgs field of this one. So there is no delta action over V prime. So over this, via this explicit, this is something like Ci times K times phi partial I. So we have another one, and also we can have, because we have another descent. So that we can do a explicit computation from these explicit isomorphisms to compute from each other. Yeah, and the cruel thing is that this Hilbert ring is built from the Falkins extension, and Falkins extension, as we have seen, it unifies all possible system coordinates. That's the philosophy allows us this computation will work.
So you mean that the in your main theorem, so starting extension appears, and then the reason is that in the hot state period ring.
Yeah, this is one of
directly related.
Yeah, directly related.
How about you?
Yes. So I have two questions for the two parts. So maybe we start with this since it's already on the blackboard. So you have this very nice comparison between the structure sheaf on pulping side and the structure sheaf on this other sort of V side. Okay, so starting from the structure sheaf modulo P, you can construct other period rings, right? Like A-inf or A-cris. So I guess that from these you can also get descent results for these other period rings.
Yeah, for A-inf, yes. But I haven't considered yet the crystal. But for A-inf, I think it's relatively easy. Yeah. Okay.
And if we say believe that maybe also for a cris it works, you think that this could also maybe provide a way to define the notion of when sort of a least p-adic sheaf on the generic fiber is crystalline, even if you have, I mean, you have a very bad model using the same idea of maybe passing to some semi-stable hypercover using some descent. You think that could be possible? Because that's one of the main obstruction to consider, right? Good subcategories of least sheaves on the generic fibers, the existence of good models. You use that to define these subcategories. And could these descent results that you prove allow to get more general coefficients also when you have bad models?
Actually, I didn't think, I haven't think about that yet, but I think we can consider some, let's say, we can replace the Barton's ring topos. Let's say this is somehow, this is the fiber site of X that we may consider more general, like let's say we may consider the H topology of X, and we can produce each fiber is finite data site of its geometric generic fiber. So we may call it EH Y2X. And we know that this result says that for every perfectoid object in it, the cohomology behaves very well. And we can produce some period sheaf over this side, and we may do something. Yeah, but I haven't think about too much.
It looks very interesting to me. So, also, so concerning instead the first part of your talk, I would like to understand from you how much you can sort of relax the hypothesis in the theorem that you relax the hypothesis that
hypothesis
you have in your theorem, right? Because, for example, it seems already that you can not only require that A0 admits this étale chart, but you at some point you allow, for example, localization, right, to get the height 1 points. That's one operation that I think still fits in your theorem, right? And can you get also other operations, like, so for example, completing along some ideal, even the ideal P?
Yeah, in my thesis, I didn't consider too much operations. So first, we have such a standard ideal semi-stable chart, right? A0, and what I allow something like so first, as I said in the talk, I allow generically finite ideal extension, and I also allow. So this is the first case, and the second case I allow admissible blow-up. Yeah, and thirdly, we have a localization. But in principle, I think
It should be possible, right?
it should be possible because a lot of arguments are relying on Tsuji's work, and Tsuji's work in Tsuji's work we have the Henselization. We allow Henselization. We allow p-adic completion.
Mhm.
But in my work, I only consider the simplest case because it's already very technical. Yeah,
Okay.
but I think in principle we can make them all work.
And one last question is about the coefficients. So you had this 5 projective right coefficients, but I think in your thesis you considered also more general coefficients.
You mean sense theory?
Yes, yes. I mean, for example, can you allow some sort of Banach modules?
Yes. In my work on sen theory, I extend the sen operators to some infinite dimensional representations. So the idea, the philosophy is this: how to treat the infinite dimensional representations. So in fact, in my work, I consider something like this. So we still consider this. Let's say if we have something L in our K infinity, we have K, such that this L is a p-adic. So the Galois group of L over K is a p-adic analytic Lie group. P-adic analytic group. Then for every representation, S of G with coefficient in QP, finite dimensional. Then we proved that its sen operator has a universal expression. I mean, there is a sen operator lies in which is an endomorphism from the dual of Artin's extension to the Lie algebra. The bar hat tensor with Lie algebra of G. Okay.
Tensor over
QP, yes. Such that the sen operator of this over the sen operator X over S tensor over QP. So we have defined the sen operators over these representations. And then in fact, I said for such representations, we can lift this to that. Because over this side, we have a natural infinitesimal action of this X on this. Okay? So we proved that for such representations, the sen operator has such form. So we have a universal morphism of Lie algebra such that this will give us the sen operator. Okay, so how to extend it to infinite dimensional representations? You see this part, if we can make sense of it to act on an infinite dimensional representation, like some Banach representations, if we can have this Lie algebra act on an infinite dimensional representation, then we can always say that first is how the sen operator is defined. It's defined via this morphism and the action over that Banach representation or infinite dimensional representation. Okay, so once this can be defined, then we can always extend our sen theory to that case. So the question is that how that operator relates to the operator we have already defined. So we need some assumption on the Banach representation. Let's say if the finite part is dense, so that we can approach
which part is dense?
Finite part.
What do you mean finite part?
So for example, if we consider S, which is an infinite dimensional representation of G.
Infinite dimensional over, you mean over QP?
Over QP, yeah. We may consider the G finite part. Yeah, something like this. If this is dense in here, we can compare. We can somehow use our previous theory for finite dimensional to see the extension of Selm operator, which properties they have, like this. So I think this is the philosophy to extend it to infinite dimensional representation. Yeah.
Thank you.
Okay, maybe offer.
Also, there was a question when you stated this, so it seems closely related to Scholz's work, also primitive comparison
Yes.
theorem. So in fact, your faulting side is kind of an approximation of the rigid detail topos. So in some sense, you are, since you locally get enough finite detaching locally give you perfectoids, you have this KP1 result of Scholz's and Atchinger also. Then you have the kind of the cohomology of O bar module P O bar. I mean, the tal cohomology is the same as the one on your topos because you get perfectoid. Because your topos is enough to get perfectoid, and you have the theory of well, maybe I get it. So in fact, one can deduce one can deduce this also from the more general primitive comparison theorem, I suppose, without.
You mean we can deduce this theorem from Scholz's comparison theorem?
The primitive, so-called primitive comparison theorem. In his paper on in his third paper on.
Yeah, so first of all, we always slice in the schematic language, right?
Yeah, but in fact, the rigid, so there is a comparison of the cohomology with the rigid detail cohomology, which is already done before.
Yeah, but before, do we need some notary condition on that?
But no, but the for what? For
the comparison of rigid cohomology of rigid analytical varieties with the another cohomology of schemes. Do we need some notary condition or working only over the valuation ring of height 1?
No, I think it is an evaluation. Yeah, I say I'm working over evaluation ring of height 1.
Yeah.
So in your case it is evaluation ring.
Any evaluation ring, but it's somehow easy to reduce to the valuation ring of height
it seems that you have the canonical localization of height. I mean, you can so even not p-adically separated and not. Okay. So there is. I did not. You can have a higher rank thing which is even not p-adically separated.
But in fact, for this theorem, because we only consider the finite locally constant shift, so we can reduce very easily from the general valuation ring case to of height 1.
Okay. Yeah. And then in the height 1 case, so
that's in the height 1 case we have that.
And then in the height 1 case we have anyway, we have comparison, and then we have the more general work on in the rigid setup, which imply this.
Maybe for this, because we only consider finite locally constant shift, maybe this can be deduced from Scholz's primitive comparison. But in my thesis, I generalized it to torsion abelian coefficient in the following form. So the R gamma of this B sites, and I consider, so let's recall that we have a comparison morphism covariance scheme over Y, and we have the comparison to my things. And I consider such the following shift, the curly F, which is per psi lower star and A inverse of F. Okay, I consider this coefficient, and
F is what?
F is this F.
Locally constant or
locally constant up to now. So first we consider the finite constant, and we try to reformulate this theorem by this B site. Okay, and then we see that this is they are isomorphic to each other. by cohomological descent of p-adic cohomology and the locally analyticity of p-adic. Okay, so we have this, and on the other hand, we have our cohomological descent for Martin's ring purpose. F tensor O. Okay, so we have almost isomorphism. So we can reformulate the Martin's comparison morphism as this canonical almost isomorphism. Okay.
Okay.
So after that, we can do something more general. So after that, I say that for any f over y at torsion abelian,
Okay.
and I still consider this coefficient, and this is still an almost isomorphism.
Can we then, if we work in the rigid language, so of course there are many topologies now.
Yeah.
So at least for the rigid detail topology, you can take a sheaf. Well, maybe it should be algebraic. Let's take an algebraic sheaf passing to the rigid detail, and you tensor again with O modulo P O, and you O plus mod P O plus, and then you again you can try to formulate the same primitive comparison. Probably your result looks like very close to set this one.
I think Schwarz only Schwarz did a similar thing, and his result says that he only considered constructible sheaves over rigid analytic varieties. He has a rigid analytic version of this, and he proves for constructible sheaves. So I don't know if he can include his proof can include the torsion abelian sheaves.
But every torsion abelian sheaf has a filtered limit of constructible.
Yeah, but I don't know why he only states up to constructible sheaves over rigid analytic varieties.
In which sense constructible? Constructible on the analytic stratification?
Yeah, yes.
Okay.
Yeah, he only states for constructible sheaves in the
In this paper in 2000.
in the survey of perfectoid spaces. Survey of perfectoid spaces, 2013 maybe.
Ah, okay.
Yeah.
So it's another. Okay, I didn't remember exactly.
It's a survey.
It's another place. Yes, another. So this, yeah, of course, in general, rigid analytic sheaf is much more general than constructible. So it's sometimes it's not clear what should it be for more general rigid. So of course now we have the different topologies, the V topology, the arc topology. So all the cohomologies should be probably the same. So.
Yeah. Should be comparable to each other.
Yes, for nice things, but
for
one
nice
is to
things.
see which kind of shapes, rigid shapes are.
Yeah.
When you say torsion abelian, just a sheaf of torsion abelian groups.
Yes.
Just a p-torsion, I mean, because the other one is killed.
Yeah.
Okay, p-torsion.
But our approach is quite different from Schwarz's approach because we proved via this alteration theorem. And,
No, I understand you, but it's strict algebraic thing that sometimes people use.
So another question.
No, just I already asked in the. I have not. Is it the case that this descent, this kind of in descent theory, you said that you have E less than or equal to D, and you consider different. You assume that all the process works, that you can complete and so on. I mean, but is there a case where it's not unique that the thing that so E is less than or equal to D, and you can you have different descents, different kind of analytic, how is it called?
Delta.
You mean different descent
yes.
for generalized system
Yeah,
coordinates?
you said that for the usual one, you have a unique one, and can you have a different one?
Yeah, yes. That's in fact it's explained in the example because if you consider the semi-stable curve, it's already appeared because the special fiber. So if we consider A and the A infinity and the A infinity infinity
Yes.
defined by X, okay, defined by X, then we know that X is p-basis for one localization, but not for the other. So if we have a descent for this one, we have a representation for this and descended to this, and then we localize. Once we localize, we reach a tower which is not a standard, right?
Yes.
So that's the other descent, not the standard descent
The
of
standard would be y infinity. This is what the others. What do you mean the standard?
the standard descent is associated to the lifting of p basis.
Okay.
Yeah.
No. What I'm asking is the.
To local.
No. You had.
To generalize system of coordinates.
No. You said that you generalize. Suppose you have a whole representation delta prime analytic gamma prime k infinity go to FG k bar. So what do you know about this functor in general? So you said that in the good case it is an equivalence.
Yes.
And in general it is what? It is
in general, I don't know anything.
It's a faithful functor.
No.
Faithful?
No, I don't know.
Fully faithful? No.
No, I don't know anything about it.
Yeah, so the question was whether you can have different V prime going to
Yes,
W.
V prime and V double prime is a question. That
Yeah, this was.
Can they be different?
But can you actually get for some choice?
So two representations were not isomorphic, they became isomorphic after going to k bar flat, k bar hat.
I don't have any such example in mind. I'm sorry.
But is it natural to expect at least when equal to D, it's natural to expect that this should be perhaps an equivalence of categories in.
As I said, if we consider some generalized system coordinates, such thing we don't know if it is perfect toroidal ring or not. So such descent theory and to prove this faithfully fully faithful
in the field case.
In the field case, okay.
In the field case, I think I can show it.
Yeah, in the field case, we may show it is a perfect toroidal field.
But in the field case, is it the case that this factor is? I'm just speaking about the field case. This factor is, of course, it should be faithful because it's just tensoring a vector space.
Yes.
Then you can ask whether it's fully faithful, and or even. But what happens if you add a system of suppose you have this E less than D, you add more functions to get a full equal D, and you have this category of delta prime analytic guys, and then you can extend, you add more functions, and it goes to the category where you have more functions. And this factor, is it let us say fully faithful or something? Is it?
Yeah, in the field case, let me. So we may first consider this. As you said, this is a perfect toroidal field, so this should be an equivalence.
Yes.
And now we wonder if this is also an equivalence with the condition. But technically, I think the proof for the equivalence of this is relying on the only proved for taking the lifting of p basis, and I don't know if the argument will work for general thing.
Yeah. So my question was whether if you add more functions, the category of delta prime analytic of Left delta, analytic,
Yeah.
gamma phi. So this category, when you add, how does it behave when you add more functions? When E is less than D, you add more functions. Is it a functor which is fully faithful, or it's easy to? It's the same K infinity. So it's just the
Same K infinity.
Same K infinity.
Only this change.
Yeah, only the gamma changes, so it's clearly fully faithful by definition. Okay, so it's clearly a subset. Okay. Well,
Okay. So I have one question. Well, lots of questions have been asked. Can you say a bit more about this generalization of Lupin's results? The cancellation of locally analytic vectors.
Yeah. So let's consider this setting. We have L, we have K infinity, and we have maybe we can consider more general. Consider the fraction field of A. So this is the fraction field of A. We consider L infinity, and in the middle we consider something like this. And they are included in the maximum unverified extension. We have G. We have the curly G. Curly G is a p-adic analytic group. So in this case, we have already have a universal same operator from the.
So you could be equal to G, right? It could be equal to G.
No. G is not a p-adic analytic.
Okay.
This is
Okay. So you mean it's included into some L infinity, something like that? Okay.
And we have such a canonical map. Okay, so the result is that we can consider locally analytic vectors here. Let's say we have K, we have L, and D. D is the integral closure in this extension. Then we can consider the G locally analytic parts of this p-adic completion. And we know that only for this locally analytic thing, the Lie algebra acts infinitesimally on it. Okay? And so that we can make sense of the right-hand side X on that if you extend the scalars to this one. So roughly speaking, the right-hand side X on that. Okay? So the theorem says that
G, so your script G acts on B on this V1 over P, right? So you take the locally analytic vectors.
Yeah.
Okay.
So that the Lie algebra acts
okay.
infinitesimally on it. Okay, the statement is that the image of the geometric part of the same operator. The geometric part is because this is a 1 plus d dimensional, it has a d-dimensional subspace defined by the dual of differentials. So the image of these parts, there are some linear combination of some derivations of G. So this annihilates here's this one. This is the statement.
And so not all of just the geometric part. I mean, what about the cyclotomic?
This is a technical point. I thought it for a long time, but I couldn't achieve it. I believe that we can generalize it to everything.
In Lupin's original result, which was a special case.
Lupin's original result, you only consider the geometric case.
Okay, right.
Yes. And we think a lot of arguments can work, but we couldn't achieve it right now. Yeah.
Okay.
But in the trivial case, in the case k is equal to infinity, in that case, what happens? Still non-trivial.
Yeah, in that case, let's say if the residue field is perfect, in that case, I think this is proved by Gomez and yeah. Yeah, if we have no geometric part, this can be proved, I think.
Colmez-Berger?
Yeah, Gomez-Berger.
Berger-Colmez. Ah, yeah, okay, I see.
Yeah.
Puis analyse scientifique de l'NS.
Yeah, but if we have the two parts simultaneously, I don't know how to treat it. It is very complicated for me.
Okay. Any more questions? No. On va délibérer.
Okay, so Visha, we will meet in the other room.
Okay.
We should move very quickly. We should move to the
I think they only consider complete discrete evaluation field with perfect residue field. Yeah, and they proved something similar, like but for the arithmetic part.
This is
This is a discrete evaluation field, the extension of I think finite use.
But then this is just.
All four of us are alumni.
Yeah. How do you say? We forget about this part. This part we forget about this part.
Yes.
And they consider this is a finite extension over QP.
Yeah.
And
It's just the arithmetic.
Yeah,
And
the arithmetic part.
And they consider Galois extension of L with p-adic analytic Galois group.
And they reformulate cell theory in some sense.
Yeah,
Yes,
in that case.
Yes.
And they
Ali, we should.
And they prove something like this.
Yeah,
yes.
This is.
Good.
It's
Only,
not.
we have to start because it will be too late. Yeah. We will be back in 1 hour and a half.
Okay,
1 hour.
okay.
Yes.
加油！
谢谢啊。
有那么多人来提问啊？有那么多个人来提问啊？
就是这个评审委员会那个吗？
哦，
这个
你会说中国话？
一点点。
哎呀，真的。
搞点水来给他喝。
啊，好。
我有水，我有。
So they are not coming back.
They will coming back after 1 hour because they have to discuss. Yeah, discuss
So
to
the
sign
deliberation-
some documents.
Okay, it took a lot of time.
Yeah, it took a lot of time. This is a French tradition. And after 1 hour, we will have a party for the guests. Yeah.
他的中国话讲的还蛮好的。
Yeah, because he went to China many years ago.
没有，他这个有这么多问题，就有点紧张了也。
哎呦，肚子有点痛。
胃痛啊。
可能冷到了，是不是？
我把衣服加起，要不要把里面这件衣服给你加起来？
不要。
这个教授题，主要是可能有些不理解了，是不是？
没有，他都是提的很深刻的问题。
都很深刻。
那肯定啊。他当然理解，什么事情都理解的。
很厉害。
不是，这是我的论文。
他们都拿了一本了。
这里灯啊什么的要不要关啊？
他们有工作。
我觉得他们
关了吧。
有工作的。
然后就是等他们搞完。
有问题啊。
对。来，我来帮你拿包了。
Okay. Yeah. Okay. Stand here. Yeah. Over. Sit like that. Stand here. Yes. Stand here. You stand.
Okay. Dans un exposé très. So it's in French, huh? Okay. Dans un exposé très bien structuré, vous nous avez présenté vos nombreux résultats autour de la descente en théorie de Hodge p-adic. En particulier, vous nous avez expliqué votre puissant théorème de descente cohomologique pour le topos annelé de Faltings. Puis vous en avez donné plusieurs applications. Le jury a été impressionné par l'aisance et la clarté dont vous avez fait preuve tout au long de votre exposé, ainsi que par votre maîtrise lors de vos réponses aux nombreuses questions du jury lui-même. C'est pourquoi le jury estime que vous avez toutes les qualités requises pour être un excellent chercheur ou enseignant-chercheur et vous décerne le grade de docteur en mathématiques de l'Université Paris-Saclay.
Thank you. Thank you.
Thank you.
Félicitations.
Merci. Okay. Yeah, so now you are invited to my photo desk. Yeah, thank you very much.
You're welcome.
Okay. We can move to the other room.
See you.
Bye.
Just kidding.
Bye.
Just kidding.